Hi, I'm Michael Peshkin. I developed this Lightboard because I like teaching with a board, but I also like facing my students. For me, it is a familiar way to teach. There's no post-production. It's all right straight to disk, and so this process is quick. But maybe most importantly, in technical subjects, you do a lot of referring to symbols and graphics on the boards. You've got equations, this term, that term. You've got diagrams. I might talk about the voltage across here, the current through, and so on. And you teach with your hands, and I want to be able to do that easily. Additionally, I can superimpose PowerPoint graphics and then go and annotate those graphics. So if you're involved in online education or flipped classrooms or other reasons why you might want to commit a lecture to videotape in an easy way, I invite you to consider the Lightboard. Thank you. Transistors as switches. Often, you want to use a transistor in a way in which it is either all on or all off. What I've shown here is a NPN transistor, and here's a light bulb. That's a symbol for an incandescent light bulb. And we're going to say that's a 50 ohm light bulb, and it's supposed to operate on 5 volts. 5 volts divided by 50 ohms is 100 milliamps, and that's way too much current for your op amp, for instance. But it is something that the power supply of your breadboard could supply. And I'd like to turn this light bulb on and off as a consequence of a square wave train. So you're getting a signal from a function generator or from some other part of your circuitry that ranges from 0 to 5 volts, maybe with fairly high impedance so that you certainly can't use that to drive the light bulb directly. And then if the gain of the transistor is smaller than we expect, things are okay. So maybe I'll use a 3300 ohm resistor here, which happens to be one that I have. Now the base current is a little bigger than a milliamp. The collector current can't get bigger than 100 milliamps no matter what, because that's enough. 100 milliamps is enough to make 5 volts across the light bulb. 0 volts VCE is now 0 volts left across the transistor. That's as low as the voltage across the transistor can ever go. So that would be a good choice for that resistor. And now you can see that this signal that drives that light bulb really didn't have to be very low impedance at all. It's driving a 3300 ohm input impedance at least. So any old signal generator or square wave generator would be quite adequate to that, and it's enough to make the light bulb go on and off completely. Inverting versus non-inverting amplifiers. This is an inverting amplifier configuration. The whole thing is an inverting amplifier. This whole thing is a non-inverting amplifier. What that means for the inverting amplifier is the gain, which is the ratio of the output voltage to the input voltage. Here, that is going to be a negative number, whereas the gain over here, the ratio of the output voltage to the input voltage, is going to be a positive number. Now, don't get confused between these names, inverting amplifier, non-inverting amplifier, referring to the whole configuration, versus the unfortunately named inverting input and non-inverting input of an individual op amp gain. This one, it's hard to imagine how you're going to make the gain less than 1, no matter what values you pick here. And this one, you can have pretty much any value you want, as long as it's negative. Finally, let's just discuss picking sensible values for these things. You shouldn't use like 10 ohms and 3 ohms. The output of the op amp has to be able to drive this voltage divider, and you know its output impedance is like 100 ohms. So these things should be big compared to 100 ohms. And the kilo ohms, tens of kilo ohms, hundreds of kilo ohms. Same story here, but here it's doubly imperative because, in fact, the input impedances are 1. So because we're always doing low Z feeds high Z, it's really beneficial if R1 is pretty big.
Hi, I'm Dr. Kyle Montgomery, and in this problem here, we'll be looking at another operational amplifier, another op-amp circuit. Specifically, in this case, we have the case of an inverting amplifier there specifically. So then by Ohm's law, we could say that I1 is going to be equal to 1 volt divided by the 1 kilo ohm resistance, thereby giving us a current of 1 milliamp. All right. Now, similarly for I2, which is just indicated along the lower branch here, we see that we have an increase of 2 volts, and then that has to drop back down to 0. So therefore, that tells us that 2 volts from this source is going to be entirely dropped across that 2 kilo ohm resistor. And so setting up a similar equation, in that case, would be, this is 2 volts over 2 kilo ohm resistor here. Will give us, again, also current of 1 milliamps, all right? Okay. Good. And again, this was just found by writing a KCL equation here, or kind of separate here, a KCL equation right here based on this node where we have indicated V0 specifically, all right?